Okay. Now, you may have noticed that when I was talking about the left sum and right sum, I had like a really long addition. So mathematicians found it necessary to introduce some kind of shorthand for these long additions. And you know how shorthands work, right? I mean, I guess nowadays reporters don't use shorthands, but before, like hand recorders were not so popular. They didn't have those. What people did was, in the old days, like 100 years ago, they would each reporter will make their own system of writing shorthand. So if you just scribble like this, that means he said or she said. So a long sentence can be just memorized, memoized as a very short, like scribbles. Okay, so that's what we call shorthands. And shorthands have the advantage of being able to write down complex things in a very compact way, but the trade-off is sometimes when you write that when you see that compact notation, you don't know what it means. You have to figure out what it means. Okay, so there's a challenge, right? So there is something called summation notation. Also known as sigma notation, because this thing here is a Greek letter for S. So there's the Greek alphabet, which corresponds to our alphabet, and a lot of them looks like the Roman alphabet, but some of them looks totally different. So, for example, the letter S, the capital S is this. The lowercase s is like that. That's also sigma. And the reason that the S of the alphabet evolved from this was because when the letter S was written at the end, they would write it as S. So when the letter S comes at the end, they write in a different letter. So that's also sigma. So for example, there's a truth in Greek is logos. Yeah. And that's really sigma, but they don't write this sigma, they write this sigma because it appears at the end. And then later, I guess Romans took this and used it as capital S. Right? But this unnecessary truth. Okay. So what we are seeing is just the letter S. Why would why would we be using letter S?
Sum.
For sum. Okay. So this just simply means sum. Okay. So by the way, when you see pi, we just think about the circle. But for Greeks, pi means the letter P. It's just their way of writing that letter P. And this is the lowercase. The capital is like that. It's the capital P. And guess what mathematicians use this symbol for? Capital P for? This is for summation. This would be for?
Division.
Product. So for products, they use this as the shorthand. Okay. All right. Lots of unnecessary facts. It's fun to learn. Okay. All right. So this symbol is used for summation. What is the summation notation? Right. It goes like this. You have so you have a start. And you put the end, and then you write an expression using end. That's the way you use a summation notation, and an example is for example, let's say you have sigma n equals to 1 through 10 of 3n minus 2. So that will be an example of a sigma notation. A beginning point, ending point, and an expression that uses n. And this is a shorthand for some long summation. Okay? Meaning that in order to understand what this means, you really have to interpret this and write it in longhand. Okay? And that's the part that does get confusing when you first learn this sigma notation. So let's try to write this, the corresponding longhand. What does that mean? Well, it's like this. You start, n has the value of the starting value, and then it starts increasing by 1, always by 1, until it reaches this end value. Okay? And then it stops. Okay? All right, so first, when n is 1, what's this value? 3 times 1 minus 2 is 1. Okay, then you increase n by 1, so n becomes 2. 3 times 2 minus 2 is 4. Okay, and then you increase n again, so the next number is 3. 3 times 3 minus 2? 7. N becomes now 4. Next number for n is 4. 3 times 4 minus 2 is? 10. And you can see a pattern here, right? So because every time you increase n, you get 3 more. So it'll be 1, 4, 7, 10, 13, 16, 19. Right? Right, three apart. Okay. All right. So you get 22. Well, how many am I supposed to do? I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 25, 28. Okay. So these are the numbers that gets created by this shorthand, and because this sigma means sum, I have to add. So that's what it means. Now, if this was the capital P, capital Pi, then you would be multiplying all these numbers instead of adding them. Okay? So that's, but we don't do products here. We only do summations in this class. All right, shorthand, longhand. Shorthand is quicker to write. Sometimes you can see some pattern that you didn't know before. I mean, if you didn't write this and you wrote this down, would you have known that these numbers are this form? You wouldn't, right? But if you write it like that way, then you will see something that you haven't seen before. Okay? So that's another advantage. Longhand, explicit, it's clear what it is, but it takes a long time to write, and it takes up so much paper, and it's bad for environment. You don't want to write longhand, unless you really have to. Yeah, so that's what summation notation is. We still have 5 minutes, so let me show you some examples, some properties of the summation notations. Okay, properties. If you have, say, n equals to, well, I don't even want to write this down. So let's say you have some number here and there. If you have an plus bn, so an is like one of these, some expression for n. Here's another expression for n, and if you add them up, that's same as sigma an plus sigma bn. What about some constant multiple times an? That's same as constant times an. So let me give you an example. If you have say 2n squared plus 5n. This is same as sigma n from 1 through 10 of 2n squared plus sigma 1 through 10 of 5n. That's what this first rule is saying. Moreover, these constants that's in front, right? You can pull it outside. That's what the second rule is saying. You can take those numbers and put it in front. And what's the advantage of this? Well, actually, the advantage of this is that if you have like squares adding up to a certain number, then there's a formula for it. Also, if you have just certain numbers added, there's a formula for that too. Okay? So if you know that this is like adding up all the squares from 1 through 10, you can use the first formula to say it's 2 times 10 times 11 times 21 over 6. And this is like adding from 1 through 10, right? So this one's like 1 plus 2 plus until 10. So it'll be 10 times 11 over 2. So that this one will be 770, and this one would be 275, so that you can get the final answer as 1045 as the final answer. Okay? Now, this is somewhat amazing because if you actually wrote down what this summation is, then you would have had no idea that you could do such a thing. See, when n is 1, what's that? That's 7, right? When n is 2, that's 4 times 2, 8 plus 10, so that's 18. Way until when n is 10, that's when n is 10 is 250. So if you had this summation and you're told what the formula for those numbers are, would you be able to just calculate like that? No way, right? But these two properties somewhat allowed us to simplify this complicated things as sum of some simpler things so that we can apply these formulas to get it. Okay? So that's why the summation notation is preferred. It allows you to see things that you wouldn't see if you didn't use this compact notation. Yes?
Why is that first one, the first formula, over 6 and not like n or something?
That takes a while to explain, but it's really like 3 times 2. Yeah, and I'll give us next time. I'll explain why that thing holds.
It's always over 6 if you use that formula?
If you add from 1 square until n squared, that's the formula you get. Kind of amazing why it does.